Hello, from my side to our today's webinar, Future-Proof Integration of Digital Secondary Substations, on the example of the EORSys as an fault indicator and digitization unit. My name is Gerald Jacob. I'm the product manager of our product group EORSys, that means for Earth Fault Indicators and for Earth Fault Compensation Regulators. I shortly want to introduce to you our company, Eberle, here from Germany, located in Nuremberg in Bavaria. The company was founded in 1980. As I said, located here in Nuremberg at the Franken campus. We have at the moment around about 140 employees. We are active in all voltage levels, which we will see also on the next page, and we are operating internationally, as you can see here on the right side, with local partners worldwide. We are rapidly awarded and certified, so especially interesting for DSOs according to ISO 9001 and 27001 certified ISC. We are also certified as a top innovator several years, also this year, 2024, and also as a top company at Kununu rated. As I said, we are active in all voltage levels. Here is a matrix where we are located, in which voltage level with which products, and what kind of different product groups we have. So in the first two rows, you see power quality, fixed and mobile. So we have two different product groups here. The one mobile is for using these devices for a certain time, and power quality fixed, PQSys also called. These are for fixed installation in utilities. Second big row here, a voltage regulation. We offer low voltage regulation systems for 0.4 kV, as well as regulators for big transformers for the middle and high voltage and highest voltage levels. And last but not least, here the product group EORSys with Earth Fault Compensation and Detection. We have two different devices for Earth Fault Detection, which we will talk about today. And as well, we have regulators for arc suppression coils, and as an additional accessoire, current injections if the zero sequence voltage is too low or too much fluctuating. This helps to regulate the AC correctly. So this as a very short introduction about our company. Let's come to our agenda for today. I listed here four main topics. We want to talk at first about the challenges for the electrical grid on the example of Germany. I know today we have listeners from all over the world. In many countries, it's quite similar. And the second topic, I shortly talk about the differences between simple the simple secondary substations on the one hand, and digital remotely operated secondary substations on the other hand. Then I really want to give a quick overview of our Earth fault detection methods of the different devices, very shortly, only one page, and possible location strategies. Yeah. To give an introduction for listeners today who are new in the field, maybe. In the fourth topic, we will talk about the EORS3DS, which is the device that we see in digital secondary substations because of the performance of the device. And in the end, in the last chapter, we will talk about a real example where the EORS3DS here and a local utility in Germany, NetCBW, is installed and used in the digitalization or as a digitalization unit for secondary substations. This NetCBW standard is called FFU 2.0. I will tell you later what this name stands for. Yeah, at first the challenges. I think this is quite similar all over the world. More and more renewable energies getting installed in the field here in Germany. The goal is to have at least 80% of the electricity produced by 2030 out of renewable energies. At the moment, we are at a level of, by end of last year, 2023, of 56%. Then this shall be reached by increasing the installed power, on the one hand by wind power, on the other hand by photovoltaic, as you can see here. So there has to be installed a lot more. This is the generation side. On the other side, we have the consumption side. So also on the consumption side, the network gets more and more volatile because of installed heating pumps. So here in Germany, for example, it's more or less from beginning 2026 not allowed anymore to install oil or gas heating pumps. So the heating pumps will be the new standard. On the other hand, we have electromobility. So the goal of 50 million cars up to 2030, yeah, is ambitious, I would say. At the moment, we have more than 1 million cars here in Germany registered. And at the moment, the market stocks a little bit. So new cars are not registered in a high value, unfortunately. On the other hand, you need also public charging stations for these e-mobility. So here we are also behind the plan, I would say. So around about 100,000 public charging stations today, and the goal is 1 million up to 2030. Yeah, what are the challenges out of a DSO, out of the view of a DSO? These secondary substations are often not monitored at all. The grid situation, especially compared to the past, changes dynamically and several times a day. And the DSO has no influence, no remote control on these secondary substations. So let's see the difference between these simple secondary substations and digital remotely operated secondary substations. Simple secondary substations, as I explained before, have often no communication, no remote control. So if somebody wants to change the network, so switch in or switch off a cable field, a feeder, then he has to go there physically and do it on his own. On each secondary substation, on average, there are, at least here in Germany, around about 100 customers connected. And also, if you want to change some parameters, so for example, if you have a earth fault detection method and you want to change one parameter, you have to go there physically and change it locally. So this were the simple secondary substations, analog ones, and here we have the opposite, digital secondary substations. They have 4 main topics. First one, remote indication. So not only precise measurements, this is the most important one, but not only precise measurements out of these very important secondary substations are getting transferred to the central SCADA system and to a big data pool, but also a state diagnosis of the whole secondary substation is done. For example, door contacts, temperature of the transformer, temperature of the bushings, and so on. Second topic, remote control. So the goal is that the DSO gets influence on the network to have influence on the power flowing in the grid, and therefore they need remote control on the load breaking switches inside the secondary substations. Third big topic, typicals. Eberle also comes from commissioning of primary substations. I did it on my own several years, so there is everything quite customized. You go there and have, I would say, plenty of time to do the setup. With secondary substations, it's a little bit different because the amount of secondary substations is totally different. At NetCBW, for example, they have in total 25,000 secondary substations. They want to equip 10 to 20% of these in a digital manner. So 20% of 25,000 totally installed secondary substations are 5,000. And in each of these secondary substations, there are on average 3.5 earth fault indicators installed. So if you multiply 5,000 stations that shall be digital by 3.5, you come to a total number of nearly 18,000 devices in the end installed in the field. And this shall be not individually set up. This has to be standardized. You need typicals, you need defined delivery parameters and so on. So this is a big topic. It's just the goal is to have it plug and play, more or less. And the fourth topic, remote updates. So it's important because there are challenges the DSOs and also we do not know that we are facing maybe in 5 or 10 years, that it's quite important to have the option to do firmware updates and parameter updates from remote, and not one by one, but fleet bulk updates on a big amount of devices, not all of the devices at the same time, maybe. Yeah, in certain clusters, you can think about updating these devices, but that in the end is quite important. And here on the bottom, one picture from NetCBW. So their goal is to have by 2030 in total 1,200 digital secondary substations. So not the goal is, or you see, it takes a long time to reach these 10 to 20% in the end of all secondary substations to get digital. Okay, let's get a quick overview about different earth fault location methods, our devices, and a possible location strategy. And this is some kind of background that makes it more easy to understand the need for these digital secondary substations. Once again, this is quite short now. We have seminars where we talk more than one day about these topics. So that is really only a very short overview. I don't want to go too much in detail. If there's an earth fault on one phase, then you have in the beginning the healthy state, then the earth fault begins. You have a discharging process of the affected line, of the affected phase, and in the end you have a recharging process. In the end, this is around about in the first 5 milliseconds after the earth faults started, and then you get into a stationary state if it was not only a transient behavior, but an ongoing earth fault on one line. So, and this recharging process and the stationary state, here we have different earth faults algorithms for. For the transient method, this is a very reliable one. There we have 2 different methods. but you can use it only one time. You can use it only in the beginning of the Earth fault. And if you want to have further information because you do some switching processes in your network, then you need these stationary state methods. And what are these methods? We see here on the next page. You can divide these location methods by the grid type. So which methods you can use in which type of grid. Mainly there are 3 to 4 different kind of grids. So isolated grid, compensated grid with suppression coils, and grounded grid. And there's also low ohmic grounded grids as well. But there's also always a question how low ohmic these grids are grounded. So as you can see in the isolated grid, there are some methods that can be used that are quite reliable. So the reactive current or reactive power method, sinus phi, can be used here, and the transient method, QU2. In compensated grids, these QU2 transient method can be used as well. And here are some further methods that can be used. But in grounded grids, in the end, you can only use the short circuit algorithm. Of course, a short circuit algorithm you can use also in isolated and compensated grid as well. And then another kind of setup or grouping you can use when you divide it by concept. As described on the last page, you have this transient. I go back one page, sorry. The recharging process where you can use the transient method, and you have the stationary state where you can use these stationary state methods. And here you can see for the transient, you can use the QU2 for transient faults, and there's also the QUI for intermittent faults, which is also transient but repeating intermittent. And on the other hand, stationary faults, and here we have the wattmetric method, cosinus phi, reactive power method, sinus phi, harmonic method, and pulse location. So I hope this gives a good overview of the different methods. On the one hand, divided by grid type, on the other hand, divided by the concept, transient and stationary. And only just to give you an impression how such a algorithm can work, you can see here the algorithm QU2, so for the transient method. Here on the left side, you see a diagram where we at first, up to around about 65 milliseconds, we have a healthy state, then the Earth fault begins. We have a transient behavior within the first round about 5 milliseconds, and then it goes over into a stationary state. And the algorithm in the devices, they build or they integrate the current over the voltage, over the time, and in the end we get an electrical charge over the zero sequence voltage. And as you can see here 3 different lines. In this example, the first feeder A is the affected line, and B and C, these are the healthy feeders. The healthy feeders in the end have a straight line with a positive gradient, and the affected line in the beginning has also a straight line, but with a negative gradient. And then in the end, it's getting a little bit weird, some kind of line, so some kind of rotation. For a very high ohmic faults, this line is quite short. So there's another criteria for very high ohmic faults that can be also used to calculate this rotation. Yeah, that was only a short example just to give you an impression how such algorithms can work. Every algorithm is working a little bit differently. And now I want to show you different applications and different devices from our side. So on the one hand, the primary substations, where our Eberle also comes from, out of primary substations with our regulators for transformers and arc suppression coils. And here we have also dedicated devices, EORD, for earth fault detection, which is only working together with CDCTs, but can overlook at the same time 4 feeders. Then we have the EOR3DS, which can be equipped also with additional adapters for classical measurement values. That means 100 or 110 volts and 1 or 5 ampere. This device can be also used, for example, in a primary substation. But today we want to talk about secondary substations. We have these digital or main key secondary substations where we see the EOR3DS because of the power of the device regarding communication. And on the other hand, the simple secondary substation. Today, we want to focus on the digital secondary substation, so on the EORCDS, but I just want to shortly mention the EOR1DS, what the device can offer. As you can see, the device can be ordered together with these 3 Rogowski coils that can be easily retrofitted, but it is also capable of low power sensors. And here only just a short overview of the device. The device has also a directed and non-directed earth fault and short circuit indication, has also fault records on board and logbook functionality. The fault records and the logbook are saved on the internal SD card, and you can easily dismantle the front plate here with this screw. Behind the front plate, you find the SD card. So if you're interested in a certain fault record or logbook, then you can take this SD card and take the fault record and logbook on your PC. It is a device for switch panel mounting, has 4 relays, 2 binary inputs, is capable not only for current measurements via these 3 orange Rogowski coils. It can also measure the voltage parallel to a VDS system. So you might know a Captis or Vega device, for example, a voltage detection system, and can measure the voltage in parallel. But not only these 2 options are possible to measure current and voltage in a not so accurate manner. The device is also capable of these low power voltage and current sensors with measurement class 0.5. And then it also makes sense to measure the power values, for example. These power values can be, and all the other indications can be transmitted via Modbus RTU protocol. So the device has only 1 protocol. It has no software, but via the SD card, you can easily copy parameter setups, or you can order these devices pre-configured from our side. As I said, the device offers power recording. It has a wide range power supply for AC and DC, and it has internally a long life capacitor for at least 4 hours of indication. But this is really calculated for a time 50 years after installation, and if you are using an indication lamp in addition, so the time is normally much longer than 4 hours. Okay, this was only just to introduce to you our device EOR1DS for simple secondary substations, which is a quite attractive solution for these stations. To the EOR3DS, we will come in the next chapter. Now I just want to shortly introduce to you the strategy that a lot of DSO are using together with these earth fault indicators. As an example here, a bus bar with 3 lines. The first line is just a single feeder, and then the two first feeders are switched in a ring manner, as you can see. And we have an earth fault indicated by this arrow. So the indicators that are installed here directly at the beginning of each feeder, they indicate at first in the third feeder, okay, I see an earth fault backwards, and the two indicators in the first and the second feeder, they indicate, okay, we see an earth fault in forward direction. So this line, this ring might be 30 kilometers long. The DSO is interested in locating the earth faults in a smaller manner. So they open the ring. One remark, all coils should be in the back of the fault, so it's ideal if the arc suppression coil is located here at the bus bar. The indicators now use not the transient method, but now they need these steady state, stationary state methods to do a location afterwards, after the beginning of the fault, when the transient behavior is not present anymore. So the DSO opens here this switch, and the indicators change their direction. The one in the second one still indicates into forward direction, but the first one indicates into backward direction. So in the end, the DSO now knows, okay, the fault must be here on these two segments in this line, and in the end, he will switch in this breaker again, open the other one, and now he can see that the fault is not in the first segment, but in the second segment. So now he can send out his staff to really find the fault in the field, maybe only on a line which is 1 kilometer long or something like this. And as I said, the narrowing here by to get out the faulty feeder in detail, this is done by these stationary state algorithms. This is not done by the QU2 or QUI method. Okay, I hope that helps you, this overview, to see the demand for these earth fault detection devices. And now we come to the advantages of the EORCDS compared to an EO1DS in the application of a digital secondary substation. So the EOR3DS, as you can see, is also capable of low power sensors, and it has 3 digital value-added functions, as we call it. On the one hand, the device has not only a serial protocol like Modbus RTU, it has this as well. It has a lot more serial protocols like 101, 103, DNP via RS485. This is all possible, but it has a lot of different SCADA protocols based on Ethernet. So for example, the 104 protocol, 61850, at the moment only 61850 Goose, Modbus via TCP, DNP3 via Ethernet, and the 2 latest protocols we implemented based on MQTT. The one is IoT, to get all the data into a big cloud, maybe also on-premise, or most likely on-premise at the DSO, but to have this big data possibility. And the second protocol, management and operations, as you can see here, for remote maintenance of the device. We will see that later on in detail. The device has also 2 Ethernet interfaces on the back. The one is can be used, for example, for remote maintenance. The second one for the SCADA connection, but everything can be done also only via one port. So it's just an option to have a second Ethernet port as well. The second Ethernet port is always available, but can be enabled by license also afterwards. Security features. So you have to know this device is completely based on Linux, and we can take all the offered IT security features out of the Linux world for this device. So we have encrypted communication, including certificate handling and so on the device, a consistent role user model. So a lot of work and development is done regarding IT security here. And for the switching application, the device has 4 monostable relays on board and 6 binary inputs for getting in the information from the earthing switch and the load breaking switch. And it has some of you might know our regulators, RegD and RegDP. They have these background program possibilities, so that means a PLC functionality, and our EOR3DS has the same possibility. So you can also equip the device with customer-specific applications, like the switching. From installation point of view, there are different options. I want to start with the middle. So this is a DIN rail mounting options with additional adapters. So this is possible, especially for, I would say, primary substations. And you can, of course, install these devices in compact switchgear stations. Here on the left side, you see an example without the front plate of an ABB switchgear. You can see here the VDS system, and there's always a space left for such an earth fault location indicator. And here the device could be installed. On the right side, you can see here a compact switchgear station of Siemens that is also used in that kind of manner at the NetCBW project or standard. And as you can see here, there's also a spare place which could be used by the device, but NetCBW said, no, we want an additional low voltage compartment here on the top with doors in each cable field and in the transformer field where we can insert a local remote switch and the devices, and also an internal switch as well, which is mounted in here. Yeah, the device from the measurement point of view, so sensor point of view, there are different options. We try to be compatible with a lot of different manufacturers of these sensors. So I want to mention Zelisko, Greenwood Power, ABB, 3M, as well as Siemens. And as you can see, there are sensors offered from these manufacturers in 2 different manners from the connection side of view. So on the one hand, they have low power sensors with 2-wire connection. And on the other hand, there are also sensors on the market with RJ45 connection. And these RJ45 sensors are mainly from ABB, Siemens. They offer bushings with integrated low power sensors, as well as, for example, as you can see here from ABB, also for retrofitting, so separate voltage and current sensors. And the newest one is also 3M, which we will see on the next page. And as you can see here, we have different kinds of devices on the back. So on the one hand, for the 2-wire sensors, we have a big plug with 26 terminals to install some binary inputs, but all these at least or in maximum 4 voltage inputs and 4 current inputs. And on the other hand, the device is also available with 3 RJ45 terminals for example, 3 Siemens SI bushings. What else can we see here? The X1 is the terminal for relays. X2 is the terminal for the supply voltage, which is only DC from 20 to 148 volts. Then we have X4. X4 is the terminal for RS45 connection. This is an option, so you can order the device with or without this terminal. Then we have two Ethernet ports. You might wonder why it's called ETH0 and 2. Where is the 1? The 1 is on the front, so you can also set up the device from the front with a certain adapter. Then we have a PE connection, an SD card where the logbooks and the fault records are saved additionally. And in the end, we have here X6. It's also difference because here we have 2 binary inputs, and the other 4 binary inputs are located here on the big terminal plug. And in the other option, we have all 6 binary inputs here on this 8 terminal plug. Yeah, and here, once again, an overview of the different options of 3M. So 3M has also different sensors, as you can see here, that are also compatible with EORSys and our device EOR1DS. So the one for EOR3DS can be equipped with RJ45, for example, quite nice solution to have this multi-contour voltage sensor fed through the current sensor, and then for one phase, current and voltage comes via RJ45. At the EOR1DS, you have to connect these via 2-wire connection. So there are all possibilities available here. Only 2 pages for the sensors of ABB and Siemens, because ABB has these bushing sensor or bushing with integrated sensors and the single sensors on the market for a long time. And unfortunately, the standard changed and it changed the pinning of the connector. So at first, the current was on the pins 4 and 5, and now it's on 1 and 2. But you don't need to take this into account with our device, because we internally short-circuited 1 and 4 and 2 and 5, so you can use both variants of these sensors. In total, these sensors are class 0.5, so they have an inaccuracy of 0.5%. The device itself has also an inaccuracy in a temperature range of 80 degrees of 0.5%. So in total, sensor plus device offers an accuracy of more than 99% of voltage and current measurement. And shortly compared to the Siemens SI bushing, this one is newer. This one is only available regarding the new standard 61869. And as you can see here, the pins for the current are already on the first and the second pin. And in addition, we have here an PD100 internally integrated in the Siemens SI bushing, and the device is able to measure on all 3 phases the temperature, the internal temperature of the bushing, which is quite helpful, for example, for the asset management. And one big advantage of the Siemens SI bushing I also want to mention, this is that XWorks, the devices, come with a so-called sensor configuration file. So you have for each sensor to meet this class 0.5 accuracy, you have an amplitude and a phase correction factor. And these factors for all voltage inputs and for all current inputs are given by Siemens in one file and directly EORSys played on the device. So the device has not to be afterwards configured in any type of or in any manner, but it already knows the correction factors for each phase, for each sensor EORSys. And this is quite important. If you remember the third topic on the slide where I showed the requirements for digital secondary substations, this was called typicals, so standardized. And here the customer, the end customer, don't have to care, don't have to set up each device individually and set up at least 12 correction factors in each device, but this comes EORSys, so quite helpful for the end customer. I just want to mention we have also adapters in our portfolio for primary substations. The devices are designed for secondary substations, for low power sensors, but with these devices, the EORSys can also measure 100 volts, 110 volts, and 1 or 5 amperes if you want to use them in a primary substation. And as you can see here on the right side, we are working at the moment at a more modular solution. So we got the feedback that the current solution you can see on the left is not so nice. The customers, they want to have different opportunities, longer connection cables, and so on. So by end of the year, we will change these adapters to a modular version where you can mount, for example, voltage and current sensor on the device directly, or also in a manner that the adapters are mounted on DIN rail, for example, and you have a 3-meter connection cable to the device that is mounted in the front panel. Some words about protocols. I also already mentioned all the protocols the device offers. So not only serial protocols, but also Ethernet-based protocols. And I just want to emphasize here that regarding the serial protocol Modbus RTU, the device can also act as a Modbus master. Not only for EO1DS devices, but of course this is the solution we always mention. So if you have an application where you want to use, for example, 104 protocol without an RTU, you could use it in such a manner that you install one EO3DS as a Modbus master that offers 104 protocol and offers in addition Modbus master reads out all the data from the Modbus slaves and acts as a SCADA gateway in the direction to 104 protocol. At the moment, it's limited to up to 6 slaves. This could be also extended if required, and it's not limited on Eberle devices. This is just an example. You could connect really every device that speaks Modbus RTU. So for example, we also offer extension modules for binary inputs or binary outputs if required. If you have the wish to have more than 6 binary inputs, there are standardized modules on the market, I/O modules, that can be easily connected via Modbus master. Yeah, core competence, I already talked about that. The device has a lot of different earth fault and short circuit location methods on board. And I want to mention that we are also working on new earth fault location methods, but this takes always a lot of time and development to get it ready. And PLC functionality, One example I mentioned already, this is the switching functionality. So by the switching functionality, for example, the earthing switch is monitored. So the earthing switch must be switched off so that the load breaking switch can be switched in. So there's some kind of security feature, additional security feature. And there are some special other functionalities implemented by that way. Other examples would be crosswise calibration. So if you do not have in every single feeder a very precise voltage measurement, you could also share information out of one field with other devices from other fields. Another example would be the calculation of the total power. So if you have, for example, 4 devices installed in all cable fields and you want to calculate locally already, so some kind of edge intelligence, the total power of the secondary substations, this would be also possible. Yeah, a short overview, like I showed you from the EO1DS. So we have all earth fault and short circuit methods on board, directed and non-directed. We have fault records and logbooks on the device available, of course, and they can be also read out via software. So we have a dedicated software for the EO3DS. It has 4 relays and 6 binary inputs, which is quite important to fulfill the switching requirement in these digital secondary substations. We are compatible with a wide range of low power sensors, even more than with the EO1DS. So you remember EO1DS was only capable of sensors with 2-wire connection. The EO3DS can also connect these sensors with RJ45 plug. We have PLC functionality. We have a really wide range of SCADA protocols. Last but not least, also these 2 MQTT protocols that we will see in the last chapter. And we have on the device only a DC wide range power supply, because in the device is meant for digital secondary substations, and in these digital secondary substations you always find an uninterrupted power supply. So here the need for AC supply is not so high, so we decided only to have DC power supply. So this was the introduction of the device in a short manner. Of course, there are further details I could mention, but we want to be finished in 1 hour. So in the end, I want to now show you the NetCB W standard FFU 2.0, where our device EORSys as an earth fault indicator is used. FFU 2.0 means in German, FF means remotely indicated and remotely controlled. U means secondary substation, and 2.0 indicates that there was also a first standard that was not satisfying, obviously. So they made up a new concept. So this is a second improved, more sophisticated concept now, FFU 2.0. Here are some pictures from the first station installed, which was officially introduced by NetCBW in April 2023 in the near to Stuttgart here in Germany. And as you can see here on the right side, this is Andreas Hettich from NetCBW, who was also quite active in LinkedIn, for example, but now changed to Transnet BW inside of Germany, so another utility. And in the back, you can see now the compact switchgear station from Siemens in the complete concrete housing. And as you can see here, our EOS3DS are installed. Here the VDS systems are installed. So this is only the door on the one side. when you have a look from the other side, you can see here the transformer with a lot of also sensors on the low power side or on the low voltage side. And there are also two other sides left where the low voltage feeders are located and the RTU and so on. And the uninterrupted power supply is being installed. Let's say BW in the tender, they required a so-called process interface and detection unit. So this indicates they looked for a device not only being an earth fault and short circuit indicator, so in a detection unit, but a process interface. And what do they meant by that? What do they? What was the intention by process interface? The device that they looked for should be not only capable of location and simple measurement, but they wanted to have precise measurement and also this remote switching functionality, of course. They want to have access in these very important secondary substations and critical nodes in the grid to have remote access on the load breaking switches. The devices should be compatible with available, precise, and economical low power sensors. They wanted really to have such bushings with integrated sensors from like you know from ABB or from Siemens. The demand was to have several SCADA protocols in parallel. We will see also on the next page. So the data from the devices should not only be available in the central SCADA system, but also in other systems in some kind of IoT system, for example, for asset management and grid planning. The complete station is completely Ethernet based, so they really have no analog protocol, no Modbus RTU. There's a big difference to the E.ON concept here in Germany. That is digital until the RTU, but under the RTU in the direction of the earth fault indicators, everything is in a serial manner. Here, this concept is totally different. Every device is connected via Ethernet and has to support the regarding IT security features. Of course, it has to be a compact design, like you might know also from our competitor devices, and the same form factor as the VDS systems are made and are available. And a really big topic that persuaded also NetsBW to use our device, future-proof hardware. So we will see in the next page, the devices can be updated regarding software and regarding parameters, especially regarding software, regarding firmware. If you want to roll out new features in 5 or 10 years, the devices have to be designed in a way that they have further capability. And a lot of devices from our competitors, they are only microcontroller based, and they are designed that they can fulfill exactly what they are meant for. But they are not designed to have further features updated in future. And our device based on Linux has this capability. So a lot of resources are left in to add functionality. And in the end, scalability. Thousands of devices shall be delivered with QR codes, with certificates and so on. So you need also to prove that you can deliver in such a high value the devices. Now here, the concept out of the view of the middle voltage only. We will not talk today about the low voltage side. This is the middle voltage side, the compact switchgear station in this example from Siemens. As you can see here, it's a compact switchgear station with 1 transformer field and 2 cable fields. In the cable fields, we have the Siemens SI bushings installed in every phase. They have an RJ45 plug. These 3 plugs from each cable field are easily connected and plugged into each EOR3DS device on the back. Every cable field has a motor control unit, so the switching operation is done in a way that the command comes from SCADA, goes via the RTU to the EOR3DS. The EOR3DS compares everything, does the security features, and in the end, if everything is okay, sends the command via relays to the motor control unit, and the motor control unit switches in or out the load breaking switch. Yeah, I wrote in here through true all digital substations. So what does it mean? The EOR3DS is mounted really in every single feeder, also in the transformer field. This is interesting because in the transformer field there is no measurement installed. So the EOR3DS in the transformer field is really only used for the digitization of 6 binary inputs. So of the load breaking switch, the earthing switch, and 2 further information. One of them is the gas alarm of the whole station. And it's the same in the cable fields. Here we have also the load breaking switch and the earthing switch, and 2 further information that are wired to the binary inputs 5 and 6. So all analog signals, binary signals as well as the measurement, are digitized locally in each field. And this you can also see here in the transformer field. You see here a Harting connector. This is only supply voltage, and the only further connection are here 2 Ethernet cables. So a redundant Ethernet connection. There is no other connection to the complete secondary compact switchgear station here on the secondary side. What else we can see here, and that is what I want to emphasize especially on this page, are the 3 Ethernet-based protocols. So we have each device speaks and communicates to all of these 3 heads, yeah, to the central SCADA system via 104 protocol to the control center. Here the measurements, the earth fault and short circuit indications are transmitted, as well as in command direction the switching operations. Then we have the second path, blue path. This is IoT or IIoT, Industrial Internet of Things. So this is not in the cloud, not in the internet. This is locally installed on premise, so in the network of NetCBW, but they wanted to have a separate access for grid planning, for asset management, where they can subscribe all these different data out of these secondary substations. The reasons for that we will see then on the last page, what they are using these data for. And last but not least, the green path, management and operations. Here in the head of this management and operations path, we have a central IoT software, and this central IoT software is used, as you can read here, for remote maintenance on the one hand, so you can read out, for example, the logbooks or the fault records and so on, but also, and this is a main aspect, rollout of firmware and parameter updates. So you can easily here update all the devices in clusters remotely. So this is a very nice feature and very helpful, and already used by NetCBW to extend the functionality of the devices. Yeah, in between, as you can see here, is also a EST server. You can see it by that sign. This is a certificate server because the two protocols based on MQTT, they are protected and encrypted by certificates. This I will also describe in detail on the next page. And the EST server, so that means enrollment over secure transport, is used to automatically refresh these certificates, because certificates always have an end date, and you as a user don't want to update these manually, so the EST server is automatically updating these protocols in the field on the devices. We have in between an RTU and IoT gateway. This is for 104 netting, so to individualize the data points, and the IoT gateway on the one hand is collecting a lot of further information, as I mentioned, door contacts, transformer temperature, low voltage measurements, like the voltage and the current, and is also doing some kind of netting. So here we are not talking about data points, but about topics, and these topics, they are also individualized depending where this secondary substation is installed. Yeah, our device is compatible with two different IoT software solutions. So this is the green path when you remember the last page. The one is compatible with IoT software called Cumulocity IoT from Software AG. So this Software AG is a company that offers this solution. And on the other hand, our device is also compatible with a open source alternative called ThinkSport. So Cumulocity is used as NetCPW. ThinkSport, for example, is used in Austria at EVN utility. Just to show you how automized this process is, I designed this page to describe how the two-factor authorization is done during commissioning of the secondary substations. So each device in the secondary substation, also our earth fault indicators, they have a QR code on the side with a lot of information. NetCPW has an own app developed to scan this QR code and transfer this information into their central system. And these information are also shared with the EST server. And out of the QR code, an so-called client ID is built. The client ID you can see here on the right side. This, for example, underscore Eberle minus PIDU underscore cable fields underscore 1, and then in the end the serial number of the device. So this is the client ID, and this client ID is also part of the certificate. Each device has a certificate already being installed by delivery. So we upload this certificate before delivery, and the client ID is compared. It's checked whether the certificate is being trusted, because the CA, so the certificate authority, is signed by NetCPW. And if everything is fitting, then the device gets, in addition to the manufacturer certificate, and operator certificate. So the EST server checks all this information, and on the device automatically an operator certificate, a second certificate, is uploaded. And with this certificate, the devices are able to connect in the end with these two paths, M&O and IoT. And the devices, especially on the green path, automatically onboard on the software, so nobody has to manually onboard them and include them, but that is done in an automatic manner. Here you can see how this rollout of firmware and software is done. So we have an own software called AE Toolbox. Here you can really set every single parameter. And in the end, if you have tested such a parameter setup with SCADA settings, with earth fault and short circuit settings, and so on, you can create a complete package by this option M&O export. And then you get a zip file, and this zip file is uploaded in the Cumulocity IoT software and then can be rolled out to a lot of different devices at the same time, for example. As I said, or as written here, this is for maintenance, so you can roll out these firmware updates either on single devices, on all devices at the same time, also, or in certain clusters, so in certain groups of devices. And this is a big difference also to our competitor devices. We limited the certificates to 5. The competitors, they often had discussions with NetCPW whether a second certificate is really necessary, and they said yes, of course a second certificate is necessary because we have to upload a second certificate before the actual certificate is running out. So we said, or we talked to NetCPW and said, how many certificates do you really need in practice? And they said 5. And so we said, okay, then let's offer one producer certificate, manufacturer certificate, in addition up to 5 operator certificates. Yeah, to give you some impression what further features are available via this Cumulocity software, you can do remote diagnosis of the whole station, of the devices. You can, for example, see the temperatures of the SI bushings. You can see the connection status, so the health status. You can even see the CPU load and memory and CPU temperature and so on. So some really detailed information. You can read out logbooks. That is very helpful if you have a issue with in a station, because there was, for example, a earth fault, and you wonder why the results are as they are. You can read out the logbook remotely. And if something goes wrong, it's also possible to do some kind of reset with customer-specific parameters. This is also possible. Yeah, and ThinkSport, as you can see here, just a short example, is looking just more or less the same. You have also a dashboard, and you can create different dashboards as you want them. For example, here memory, CPUs, CPU usage, heartbeat, and CPU temperature over the time over different devices. So here can be done a lot of applications in an individual manner, and it's used, for example, here at EVN in Austria. So in the end, of course, after all these technical details, what these devices offer, in the end, it's of course important to know why we as a customer, as a DSO, should install and go that way in the direction of digital secondary substations. And here are 3 of the main arguments for doing that. First one, state estimation. So this is something that is now also done at NetCPW. They want to have an overlook of the complete grid. They do not have this at the moment, and they want to have state estimation for the complete grid out of the information they get from these digital secondary substations. So state estimation for not measured grids based on comparable measured grids. And therefore, of course, they need precise measurement data, and it's not enough to measure quite inaccurate voltage via or parallel to a VDS system. So here really class 0.5 measurements are required. Second big topic, self-healing grids. If you want to go in the direction of self-healing grids in the future, that means that you automatically detect where is a fault and isolate that fault automatically. You need to have the regarding sensors and actors in the field, of course. Yeah, you can't. You can start programming a roboter, but in the end, you need also some kind of physical roboter to take the action you are programming. And that is also one big topic. If you want to go into the direction of self-healing grids, you need the equipment for that to perform also the switching commands. And last but not least argument, cost-efficient operation. So we also do some earth fault tests, for example, with customers. And we made the experience that some of the customers during such earth faults tests, they realized that some of these parameters are set wrongly. And then they complain, oh no, now we have to go to 100 stations and change this one parameter at all installed indicators. And that is something that is also NetCBW now facing. They also did not take into account everything in the beginning, and they are quite happy now to have this remote possibility to do parameter and firmware updates to increase the functionality to do certain adaptations. For example, at first in the concept, the temperature from these Siemens SI bushings, they were not transferred via IoT. And this is now the next step. They are now available in IoT. We can easily update the firmware that they are available. And then we do a parameter setup that also the SCADA configuration is adapted so that they are really transferred to the IoT system. And yeah, this is a very good example how to extend the functionality in future. And they have a big backlog that what they want to implement in future. So far, I can tell. And the operating costs, of course, you can't send out a lot of stuff to do all these updates. That's the reason for the remote updates. As you can see in the graphic in the middle, of course, in the beginning, it's a quite high invest because of the production back and license fees for Cumulocity IoT, for example, and so on. You need a team to care about this infrastructure and about IT security. But with increasing number of installed stations, the costs per substation, they decrease a lot. And in some countries, it's different to Germany. Germany has in total 856 different DSOs. So some big players like E.ON, like NetCBW, but a lot of cities and villages that have their own DSO. And as you can imagine, they do not have thousands of substations, so this is not a topic for them. But NetCBW thinks about offering as a service in future. And I think this could be also some example for other countries, so that big players, big DSOs offer their knowledge and their concept to smaller DSOs in future to have a comparable behavior all in the whole grid, and to also install these digital secondary substation in within the next years and not within the next decades. Thank you very much for your attention. As I I forgot initially to mention, but my colleague wrote it in the comments. You are heartily welcome to ask your questions via the chat functionality. So if you have some questions, you can now write them into the chat. My colleague will question me these questions. Otherwise, you can also write me. You can see here my contact details. So if you have any questions, please contact our local partners, our sales guys, or me directly that we can offer. Okay, Max, do you have questions coming in from the chat?
Yes, indeed. We already had questions coming in while you did the presentation. So the question number one would be, could the two Ethernet ports on the back also be used to patch several devices without the need of a switch?
Yeah, indeed, this is possible with the new firmware that we released some weeks ago, 2.16. The feature is the so-called IP bridging. So you can activate that the Ethernet port 0 and 2 are bridged, so you can just patch different devices or several devices after each other. So there's not the necessity of a switch anymore. Yeah, that's possible.
Okay, thank you, Gerald. The next question would be, is Eberle also offering the central IoT software?
No, up to now we, as I mentioned on the page before, we are compatible with our device to Cumulocity IoT and to the open source alternative ThinkSpot IoT. So this software package is not from us, but of course we have applications in the field. Our devices are tested with the latest software versions of Cumulocity and ThinkSpot IoT, so that can be trusted and used. Yeah.
Mm-hmm. Thank you. So the next question would be the last question that came in yet. So for all participants on the webinar, if you have further questions, feel free to type in the chat function or in the question function. And the last question for now would be, is it possible to set up the device also from the front in case the device is mounted above the VDS system?
Yeah, interesting question, because this was, for example, also a demand from E.ON here in Germany, because they install the device directly above the VDS system, where you do not have the possibility to get easily to the back, especially if you connect the device via Modbus RTU, then you have no switch installed, and we need an Ethernet connection to do parameter and firmware updates. And therefore, we have a small service interface on the front, which is not physically an Ethernet port, but we offer an additional adapter that goes from this service port, this an 8 terminal plug, to an Ethernet port. This is not the only adapter. We also have another adapter to have direct USB connection. So if you want to read out with a USB stick, for example, the logbooks or parameters or fall records, you can also use this second adapter to connect directly an USB stick.
Yes, thank you, Gerald. So for all further questions that arise, we will get back to you after the event. And for now, we have no public, I would say public answer questions anymore, Gerald.
Okay.
Thank you.
Then thank you very much for your attention. And as I said, if you have any further questions, then get in contact with us and have a look on our social media accounts and on our website. Thank you very much. Bye-bye.